Hello, so this is just a short video on how you might calculate the uncertainty in your value of the acceleration. So some of you might do this using error bars, and we'll cover that separately, but this is if you're given some data and you are given some information about what the uncertainty might be, and this came up on an AS paper I think last year. So I've picked some really stupid numbers to make my life easy. So we're going to imagine that we've done our G by Freefall experiment on a small moon of Pluto. So the acceleration is going to be tiny. And I've dropped something over a distance of 100 millimetres, and I've measured it to the nearest millimetre, so that's my uncertainty, plus or minus 1 millimetre. And here's where the numbers get silly. The time it took to fall was 100 seconds to fall 10 centimetres. And the timing device I used measured to plus or minus 2 seconds. It was a really terrible stop clock. But I picked these numbers because it makes explaining this a little bit simpler. Okay, so you could very easily calculate the acceleration. I've rearranged s equals half a t squared to be a equals 2s over t squared. Substitute the numbers in, you'll get a value for the acceleration. You can do that yourselves if you like. But I'm more interested in the uncertainty. So, let's look at what the S equals. It's plus or minus 1 millimetre. So, what we have to do when we're compounding uncertainties is if in fact things are multiplied together like the t is, or they're divided by each other, the rule of thumb is that you add together the percentage uncertainties. So you turn your absolute uncertainty, plus or minus 1 millimetre, into a percentage uncertainty that just means what percentage is 1 of 100. 1%. So we'd normally write that as the percentage U, percentage uncertainty, equals 1%. Now, for the time, it was 100 seconds plus or minus 2 seconds. So for this one, the percentage U, actually I should have put a subscript up there. The percentage uncertainty of the time is what percentage is 2 of 100? Obviously 2%. So we've got 1% and 2%. Now obviously, well, I say obviously, it might not be, the acceleration is affected by both of these things. So we get a situation where it might be that the displacement or the measurement of the height was out by a full 1% and our actual value of 100 was not right. And it could be that the time was as much as 2 seconds different or 2% different from the measured value. How do we combine those together? So what we do is we say to ourselves, and I'm going to move this now, slide this up, the acceleration was equal to 2s over t squared. For each of these things we add the percentage uncertainty. So the percentage uncertainty in the acceleration is going to equal, well, we ignore the 2, the percentage uncertainty in the s, so percentage uncertainty in the s, plus the percentage uncertainty in the time, but then it's multiplied by itself. That's what squared means. So you add it again. So it's percentage uncertainty in the time plus another percentage uncertainty in the time. And you add all those together and it comes out at 5%. Now often, telling someone that there's a 5% uncertainty isn't that informative. So what you would then do is turn it back to an absolute uncertainty, and you would look at your value of the acceleration that you'd calculated, say what is 5% of that, and then write plus or minus that value. I'm not going to do that now, and that's it. So thank you and goodbye.